random space. Okay, so now we have sampled the input of the random space. Next, we want to go to how do we characterize the distribution of the output. It turns out that if we have a simulation or a computational procedure that takes a deterministic input and compute a deterministic output, it's pretty easy to generalize the code or computational procedure to account for randomness. Okay, so the easiest thing to do is to compute the probabilities of events. So let's say we have a solver again that takes input X and produce an output Y. And we want to compute what is the probability that that my solver, given a random variable big X, okay, is less than a certain critical value C. This is often required for accounting, for example, structural failures of, let's say, a building, aircraft, or things like that, right? So you have randomness in your materials, in your geometry. I mean, usually geometry satisfies a certain manufacturing tolerance, but you can never get deterministically what the made airplane or building is. And also same happens for materials, for the material properties that goes into the structure, right? These are all random variables. And what you want to compute is that the probability, for example, the stress when the structure is in operation, the stress of the structure exceeds some maximum threshold, right? So you don't want that to happen. And you want the probability that happens to be low enough so that you can characterize the structure to be safe. So this is when you have to compute such probabilities. Okay, and in the probabilistic method, the procedure is actually pretty simple. So you sample X to produce a set of samples, X1, X2 to Xn. And in the next lecture, we are going to be discussing how many samples we wish to produce in order to compute the result accurately enough. But the result is going to be, I can plug into the solver n times. And the output being less than C or not, right, can be characterized into a set of 0 or 1s, right? So if the solver is less than C, if the output, let's say the resulting stress is within the specified tolerance, then I produce a 1, right? So basically, I'm going to be produce a 1. If this is greater or equal, I'm going to be producing a 0. So that's basically is equal to, let's say, my II. So that's like an indicator of if this inequality is satisfied or not. So now I have produced the n zeros or 1s. The probability can be simply approximated by the fraction of a fraction of the samples in which this inequality is satisfied. And the fraction can be easily computed as, or approximated as, 1 over n times a summation I goes from 1 to n of II, right? This II is either 1 or 0, depending on if this is satisfied or not. And the sum of all the IIs are the number of samples in which the inequality is satisfied. So divided by n is the total number of samples, is basically the fraction that I'm satisfying the inequality. So this is basically the most straightforward thing to compute given random inputs. Essentially, I take the distribution of the random inputs, I sample these random inputs to produce n samples and plug all these n samples into my computational code to produce the outputs. And then I characterize the probability using the outputs. Okay, next lecture, we're going to be discussing more about this procedure. How many samples do we need? How do we compute other output quantities of interest, such as what is the mean of a random output quantity? What is the standard deviation? All right, and so I'll see you next Monday, and I'm staying for a few minutes to answer any questions.